In a place the modern world has almost forgotten, a silent operation begins. Hidden deep in the mountains, this abandoned village holds the first link in a chain. This is not a search through ruins for curiosity alone. The collectors know exactly what they are looking for. Hidden inside these collapsed structures are rare spiders capable.
What makes this operation different is not just the species being targeted, it is the level of control. These teams are trained to find, isolate, and secure only high-yield producers, using tools to detect the spiders while preserving the value of what they can produce.
The spiders are never treated as disposable raw material. They are living biological assets. Each one is selected for its silk output, behavior, and physical resilience. The first captures confirm the operation is working. But this is only the opening stage. One spider becomes several. Several become dozens. Collection is only the first threshold. Once the spiders are secured, the real challenge becomes preservation. Stress, vibration, what was gathered in silence now enters transport. The mission is no longer confined to abandoned walls and lantern-lit searches. It is becoming a supply. The village was only the beginning. Ahead lies the next stage, where isolation gives way to precision and living silk producers become part of a system built for maximum efficiency. The journey from isolation ends here. Every specimen now enters a facility engineered for control at the highest level. This is where biological potential is.
At this stage, human handling is minimized. Precision machinery takes control, ensuring that every container is moved, scanned, and verified can affect biological performance during the next phase. Before extraction can begin, each specimen must pass through strict validation. Stability, health, and environmental balance are constantly measured. The objective is simple but demanding.
This is the moment where collection becomes production. The spiders are no longer cargo. They are active components within a controlled system. Every transfer is calculated, maintaining perfect biological balance. With the spiders now secured inside controlled production units, the system is ready to begin extraction. Every variable has been stabilized. What happens next will be far beyond its original form. Production begins not with force, but with control. The system allows the spiders through silk naturally while guiding the process through balance, not pressure, ensuring consistency from the very first strand.
The challenge is not producing silk, it is extracting it without breaking the natural process. By synchronizing with the spider's movement, the system captures each thread at the perfect moment, preserving both the material and the biological source that creates it.
At scale, precision becomes even more critical. Each extraction unit operates independently yet remains synchronized with the entire system. This balance allows thousands of silk threads to be.
Raw silk is powerful, but not yet usable. Before it can become part of an engineered product, it must be aligned. This stage transforms delicate fibers into organized strands capable of supporting advanced material development.
This is where nature meets engineering. By integrating synthetic proteins and advanced binders, the silk gains new capabilities without losing its original strength.
Once reinforcement is complete, stabilization becomes critical. The material must settle into its new structure without distortion. This stage ensures that every fiber maintained for integration into a larger engineered system. At this stage, individual fibers become something greater. By combining thousands of strands under precise tension, the system creates a continuous thread strong enough to be handled, transported, and prepared for structural application. Quality control is not a final step. It is built into every stage of the process. Each spool is inspected continuously, ensuring that only perfectly aligned and consistent material moves forward into the next phase of production. Even the smallest inconsistency can compromise performance at scale. This calibration phase ensures that every fiber contributes equally to the final structure, creating a perfectly balanced foundation for the next stage of material evolution. Calibrated fiber sheets enter the advanced bonding array, where layers are precisely stacked and fused. Controlled pressure and molecular binding techniques visibly stronger and approaching its final engineered form. With every added layer, the material gains strength not just from thickness but from structure. Precision bonding ensures that each fiber can be to a unified system, allowing the composite to absorb and reinforce with extraordinary efficiency. Observe as pressure and thermal systems lock the composite structure. Real-time data confirms the fibers are settling into a stable form. The material is now smoother and stronger, achieving peak performance. Observe as pressure fields stabilize the internal fibers. Thermal regulators ensure bonding integrity without distortion. The data confirms it has reached optimal thresholds.
This test measures one of the most critical properties of the material, its ability to resist tension without failure. By distributing force across its layered structure, the composite demonstrates strength that goes far beyond traditional fibers.
Impact resistance defines real-world performance. When subjected to sudden force, the material does not fail, radiating across its structure, proving that it is capable of withstanding conditions that would destroy conventional materials.
Before final validation, the material must face the most demanding condition of all. Ballistic testing is not just about strength, it is about survival. And this straight scores delivered at extremes. Every parameter is measured before the test begins. Distance, angle, velocity, and impact point are all calculated with precision. The sure thing here is nothing here is random.
The material does not rely on a single point of resistance. Instead, its layered structure spreads the force across a wider surface area, reducing penetration and protecting the integrity of the system as a whole. The test confirms what the design intended. Instead of failing under pressure, the material absorbs and redistributes energy across its structure. This ability to manage impact is what separates advanced composites from conventional materials. What started as a fragile natural thread has now become a material capable of stopping extreme force. This is not just a test of strength. It is proof that controlled engineering can. With validation complete, the material moves forward unchanged. There's no structural failure, and also from integrated biological fibers into a composite capable of enduring extreme conditions without compromise. Strength alone is not enough. The material must be shaped into usable forms without compromising its structure. Precision cutting ensures that every section retains its full performance capabilities while meeting the exact requirements of final product design. To function as armor, the material must adapt to form. Controlled shaping allows the composite to bend without breaking, creating structures that combine flexibility with strength. This balance is what enables real-world application. At this stage, individual components become a complete system. Each panel is positioned to maximize protection while maintaining mobility. The result is not just material, but a fully engineered solution designed for real-world use. Finishing is more than appearance. It enhances performance, protects against environmental wear, and ensures consistency across every unit. This stage completes the transformation from engineered material to reliable protective surface. Protection must move with the user. This stage ensures that the armor is not only strong, but responsive. Flexibility without weakness is what allows advanced materials to perform in real-world conditions. Real-world use is unpredictable. Heat, moisture, and repeated impact all affect performance over time. This stage ensures that the material remains reliable not just once, but continuously under demanding conditions. From a silent village to a controlled industrial system, every stage has led to this moment. What began as a natural fiber has been transformed into a material engineered for protection, precision, and performance. The final test is not just about resistance, it is about real-world application. The armor must function as a complete system, responding to movement, impact, and continuous stress while maintaining full protection. The final test is not just about resistance, it is about real-world application. The armor must function as a complete system, responding to movement, impact, and continuous stress while maintaining full protection. Mobility defines usability. Protection that restricts movement becomes a limitation. This system is designed to move with the body, adapting to motion without sacrificing structural integrity or defensive capability.
Protection is measured through repetition. One impact is not enough to define performance. The material must withstand continuous force, maintaining its integrity with every strike, without weakening over time.
After every test, the result remains the same. The material holds, adapts, and performs without failure. This is the final confirmation that the system is not just engineered.
Performance is not assumed, it is measured. Every result is compared against defined standards to ensure that the material delivers exactly what it was designed to achieve. Once approved, the material must remain protected. Packaging is designed not just for transport, but for preservation, ensuring that the product reaches its destination in the same condition it was produced. Before final approval, every detail is examined at the smallest scale. Precision scanning ensures that the material has not only survived testing, but maintained perfect internal structure without hidden defects. From a single operation, a complete system has emerged. Each unit represents the same precision, the same control, and the same performance. The process is no longer experimental, it is repeatable, scalable, and ready for real-world deployment. At this stage, production transitions into distribution. Every unit is tracked, verified, and routed with precision, ensuring that the system operates not just efficiently, but flawlessly at scale.
Precision does not end at the factory. Transport systems are engineered with the same level of control, ensuring that every unit maintains its integrity from production to final deployment.
Once secured, the system moves forward. Every parameter is locked, every condition stabilized. The product is now ready to leave the controlled environment and enter real-world operation.
The journey continues beyond the facility. What was engineered in isolation now moves into the world, ready to perform under conditions that cannot be controlled or predicted. From silence to scale, from biology to engineering, the process has reached its final stage. What remains is performance in the real world, where the true value of the material will be defined.
The final stage begins where control meets reality. Every system developed in isolation must now transition into an environment where conditions are no longer predictable, but performance must remain consistent.
After transport, integrity must remain untouched. The system ensures that what was created inside the facility arrives exactly as it was produced, ready for immediate deployment without compromise.
True validation happens outside the lab. When exposed to real conditions, the material must perform without recalibration, proving that its strength and flexibility are not limited to controlled testing environments. Real-world environments introduce variables that cannot be fully controlled. The material must adapt instantly, maintaining performance regardless of terrain, movement, or external conditions.
This is the final moment. No controlled chamber, no simulated condition. Only the material, the environment, and the test that will define everything it has become. There are no controlled chambers here, no barriers between the material and the environment. This is where engineered performance faces real conditions, where the outcome cannot be isolated from reality. Every variable is now exposed. Wind, distance, and open space introduce uncertainty. The material must perform without assistance, relying entirely on its engineered structure. The difference between controlled testing and real-world impact is unpredictability, yet the response remains the same. The material absorbs, distributes, and resists with the same precision it demonstrated in isolation. Resistance alone is not enough. Recovery defines durability. The ability to absorb force and return to form ensures that the material can endure repeated impacts without permanent damage. What began in silence has now proven itself in reality. From hidden origins to engineered precision, the material stands ready, not as a concept, but as a solution built to perform when it matters most. The result is not theoretical, it is visible. Under real conditions, the material holds its structure, absorbs force, and prevents failure. This is where engineered design meets real-world proof. Verification is not only measured by data, it is confirmed through direct interaction. The material shows no weakness, no instability, only the consistency it was designed to deliver. What was proven once is now produced consistently. The process is no longer experimental. It is controlled, repeatable, and scalable across every unit created.
Every detail serves a purpose. From surface structure to internal layering, the material is engineered to balance protection, flexibility, and performance in a unified system. From its origin to its final form, every stage has been defined by precision, control, and purpose. The result is not just a material, but a complete system designed to perform beyond expectation. At its core, this is more than engineered material. It is the result of control, precision, and transformation. Every layer, every fiber, and every stage has led to this final form. Every step has led to this point. From collection to creation, from testing to validation, the process has delivered a material that performs exactly as intended. What started in silence has become something built to withstand the unstoppable. This is not just innovation. This is transformation, precision, and purpose brought together into a single system ready for the real world.
This is where engineering ends and application begins. The material is no longer part of a process. It is ready to perform wherever it is needed. Proof does not need repetition. What remains is the result, a structure that holds, a system that performs, and a material that does exactly what it was designed to do. Every angle reveals the same result. Strength, balance, and precision working together as a unified system designed to protect without compromise. From silence to strength, from origin to outcome, every stage has led to this single result. A material designed not just to exist, but to perform. Everything that could be tested has been tested. Everything that could be measured has been measured. What remains is a system that no longer needs validation, because its performance has already been proven.